Hi everyone, welcome to Chapter 5 of Learning R in 10 Days. So today, I swear, I really think this video will be short. It's all about matrices. So the manual has more of an introduction to them, and I would really suggest reading through that along with this video. I'm just going to kind of jump in. So last time we talked about vectors, and it's mentioned that a scalar has like a dimension of 0 because it's like a point. A vector has a dimension of 1, which is just a length, or it has one dimension, I should say, and it's more like a line. And so if that's the case, then matrices have 2 dimensions, right? So this is where we kind of expand upon that. And so we'll start off with a vector. It's just going to be a sequence from 1 to 6, incrementing by 1. So that's going to be assigned to A. Now, if we try to run the command dim on A, it's just going to give us null. And the reason for that is that dim can only give you the dimensions of a matrix or something larger than that. It can't give you the dimensions of a one-dimensional object like a vector. So it doesn't work on that. However, we can actually use the dim function to not only check the dimensions like we just did, but we can use it to assign the dimensions. So in example 5.1.2, what we're going to do is take that vector and we're going to reassign its dimensions. So a little bit about matrices. They have number of rows and number of columns. So what we're doing here is we're saying we want the dimensions of A to now be a 2-row by 3-column matrix. So we've set that to print it out. We can now look at it here. So remember, it has 2 rows because that's the first number we set, and it has 3 columns because that's the second number we set. So the way it works is that it strings it by the columns. So you can kind of think of it as if it were a string where it goes down one column, then starts again, down the next column, starts again, and down the last column, or so on for how many columns you have, and down all of the rows. So we can reassign this without having to turn it back into a vector. So now what we can do is, instead of having a 2 by 3 matrix, we can have a 3 by 2 matrix, setting it with 3 as the row number, 2 as the column number, and just doing the same thing we did before. Now we can see it's almost like we took this string of numbers, unstrung it back into our original 1 through 6 just string, and then strung it down now only 2 columns. That's at least the way I think of it. Okay, so that's just kind of the basics of using the dim function. I also want to point out that when we do use a dim function on something that isn't a vector, but actually a matrix, it will tell us what the dimensions are. And the way you read it once the return values is that the first number is the rows and the second number is the columns, the same way that you set it. So if you call dim on a matrix, that's what it will give you. Okay, so I did want to show that what happens when you try to give it dimensions that don't fit the length of the vector is that it throws you an error. So it tells you dims product 4 do not match the length of object 6. So it's just telling you that basically the dimensions, the product of the dimensions have to equal the length of that vector. That's an easy way to remember it. And since 4 times 1 does not equal 6, the length of my vector or string that's trying to be put into a matrix, it's not going to be able to do it. It's just going to throw an error message. Okay, so moving on, we can take a vector like we did and turn it into a matrix with dimension reassignment, or we can just from the start make a matrix. So here we're going to set a sequence, set it to B. It's just from 10 to 0, decreasing by 0.5 each time. And then we're going to take that vector and use it in our matrix function. So matrix creates a matrix out of whatever you give it. You have to give it some kind of sequence of numbers or some kind of vector of numbers. And then you specify the number of rows you want. So this one number just tells it the number of rows. And because you're specifying the number of rows, there's the number of columns necessarily follows, so you don't have to specify each. Okay, so here we have M takes a matrix out of B and pushes it into 3 rows. I will say you can also, the step of setting B first is not actually necessary. You can put it directly, you can put this sequence value right into this place of B and it will still work. Anyway, okay, so we'll set our matrix and now we can see what M is. So it again starts off with our row 1, column 1 value, and it goes down each column, stringing them all the way. Okay, so we can also check the class of M. Remember, we've been checking the class of different objects that we've made, and we can see the class of matrix, the class of M is matrix and array. You can ignore the second part for right now. Yeah. Okay, so next, how I said that it's kind of stringing it down the columns, you can actually change that. So maybe instead you want it to string it across the rows. We can do that by adding one simple term. So now we can make a new matrix N, which is a matrix still out of B. And it's still going to have 3 rows, but this time we're going to string it by the rows. And that's what that by row equals true is all about. So if we do it, we can see that now it starts off still with our 1, 1 position, but now it strings it all across the rows and then goes to the next row, all across, and to the next row, all across. So depending on how you want to string your numbers, you can just add this optional by row argument and set it to true. By default, it's set to false, so you would never need to actually write out by row equals false. It automatically does that. Okay, next we have the cbind function. So let's say we have multiple vectors of the same length, and we want to combine them into a matrix. So there's an easy way to do this without having to make it into like one long vector first and doing it that way. We can create our separate vectors, and then what we can do with them, checking also the length, right? So is length x equal to length y equal to length z. Oh, sorry. I can only do one equivalence. My bad. Yeah, so true. Then we can change this one to z. Yeah, okay. So they're all 3, I should say, equal to each other in length. So we can combine them as columns, individual columns of a matrix. So basically, U is going to be a matrix, and what it's taking is cbind, or short for column bind, of x, y, and z. So we're going to string these together almost as separate columns in a matrix, and we can see what that looks like. Okay, so x is our first column, then y became our second column, and z became our last column. And the cbind function was able to just do that quickly for us, without us having to take any extra steps. Of course, since there is a cbind function, there is also an rbind function. So if we instead wanted these to be our rows, we could just do rbind x, y, z. And we can see, whoop, sorry, I'm clumsy with my keyboard. Okay, so v is then, sorry, let me kind of get out of this because I don't want it to be too distracting. Let's remind ourselves what u is. There we go. And now v is instead our x is strung as our first row, our y is strung as our second row, and then our z is strung as the third row. And you can see that those names carry over. So because our vectors are named ahead of time, those names then get automatically applied to either our columns if we're applying them as columns, or as rows if we're applying them as rows. Okay, so cbind and rbind, super useful. Not to mention that if you already had a matrix, you can cbind or rbind another vector onto that existing matrix. It doesn't work with just vectors alone. It works with matrices and vectors, as long as they're the same length of either the columns or rows that you're trying to attach it to. Okay, so similarly, concatenating matrices, we're going to do that in the exact same way that we just did it with vectors. It works the same like I was saying. So we're going to create this matrix C. It's going to be 1 through 4, then 2, and by row. So we're going to have a 2-row matrix, and it's going to string it by row, by the rows. So we can do that. Then D is going to be not strung by the rows, but by the columns. It's going to be 10 through 7, and it's going to have 2 rows. And then what we're going to do, let's check the dimensions, right, to make sure that this will work. Great, so they're both 2 by 2 matrices, which means we know that we can attach them either with cbind or with rbind. So if we also, I want to kind of show them first. Okay, so these are our 2 matrices. We can rbind them into a new matrix like this, just using our rbind function. And you can, there's not like a limit to the number of arguments that you can put in here. So you can rbind as many matrices as you want, as long as the dimensions are correct. We're just using 2 in this example, but you can put more if you want. So then if we look at E, we can see that our first matrix C is right up here, and it's now attached to our matrix D, which is just the second half of our E matrix. So that's what rbind did. In your example, this object is F, but again, for reasons I mentioned in the last video, I am not going to use capital F or capital T as an object because I think it's poor practice. So here we have double F is going to then get the cbind version, just so we can take a look at what that looks like. And okay, so this time we cbound, we did a cbind on D and C. So our D matrix is right here, and right next to it is our C matrix. Okay, so pretty simple, good thing to play around with and get a hang of. So next, we're going to go over matrix functions. These are pretty simple, like the ones we've been doing with scalars and with with scalars and with vectors, I should say. Okay, so let's create a matrix G. It's going to be the sequence from 5 to 19, increasing by increments of 2. It's going to have 2 rows, and it's going to be strung by row. Okay, so that's our G. We can take a look at G. We want to see what it originally looks like. I think it can always be helpful. Great, so we did 5, 7, 9, 11 across the row, then 13, 15, 17, 19 across the second row, because of our by row equal true. So if we want to just check the dimensions on it, always good to do. It's a 2 by 4 matrix. We can specify, so the same way we had those square brackets with our vectors, we can specify locations in our matrix. So this is an important part. Instead of having only one number that subsets it, so it's all about like location, data location in your object. With a vector, you only have one location, right? It's just a string of numbers or a string of something else. And so by saying I want like the 7th element, it's just going to give me the 7th in that sequence of numbers or of other information. In matrices, you have 2 numbers you have to specify. you have your row number and your column number, and then this is going to give you the specific location in your matrix in order for R to be able to pull out that information. So here, what we're trying to get is the element or the value that is in the first row of G and in the third column of G. So you always specify your location with row first and column second. And you don't put any more numbers here or it won't work. Okay, so here we got, we can see actually up here in our G, our first row, our third column is a 9, and that's what it returned. So you don't have to specify both of these if you don't want. It'll give you something different. So here we're getting one specific number because we specified both a row and a column. However, let's say I only want the second row, but I want the entire row. I can do that by doing G square brackets, specify my row number, so 2, make sure you then put the comma, and leave the column space blank. So I'm not going to put anything in here for my columns, and that's basically saying I want row 2 across all columns. And we will indeed get row 2 of our matrix G. Okay, we can also perform some of the other functions that we went over in our vector video. We can do the same thing to matrices. So we can do the sum, max, min, mean, median, and standard deviation. So we'll just walk through these. Our sum of the numbers in there are 96. Max is 19, min is 5, mean is 12, and median is also 12, while standard deviation is 4.89. So again, it's just a collection of numbers, so all it's doing is applying these functions to the collection of numbers that we have. So it's pretty simple. We can also apply this to, sorry, I think I misplaced my heading. Let me move that. Oh no, maybe I didn't. Never mind. These are kind of separate though. So where this is treating all of these numbers in G as kind of just a single collection, ignoring your rows and columns essentially, the call sums and row means and similar functions to these they're going to actually pay attention to the row and column structure that you have. And they're going to do exactly what they sound like. So this is going to take the sum per each column. So if we run this, we can see that we have 4 columns. So what it did was it took the sum of each column. So if we remind ourselves of what G is, this 18 comes from adding 5 and 13. This 22 comes from adding 7 and 15, 26 from 9 and 17, and 30 from 11 and 19. So our call sums function is just adding or summing based on each column. So row means is going to do exactly what it sounds like. It is going to take the mean of the numbers in each row and return it per each row. So if we do that, we know we only have 2 rows. So the mean of row 1 is 8 and the mean of row 2 is 16. Okay, so lastly here, we have T. T just takes the transpose. So if we do that, I'm not going to get really too into what a transpose is, just because this isn't a math class and I think it might be a little outside of the scope. But if you want to take a transpose of a matrix, it's just T and then in parentheses whatever your matrix is, and that will give you your transpose. You can see what your transpose does is it's kind of like it switches the dimensions, right? So now we have 4 rows and 2 columns, whereas before we had 2 rows and 4 columns. Yeah, I would suggest looking up transposes a little more if you want to learn more about linear algebra and matrices, if that's something that interests you. Okay. So we're going to move on to applying operations to the entries of matrices. This first example is just going to show, so all our basic arithmetic functions, addition, subtraction, multiplication, division, and then also exponentiating, so something to the power of something else. We can do all of those to our matrices, and if we do them to our matrices, what it's going to do is similar to what we were doing with our vectors, right? It's going to just do the thing element-wise. So to walk through this example, let's ignore the signif function for a second. We're taking C and squaring it. Now this is not to be confused with matrix multiplication, which we are not covering. So C squared, written like this in R, just means that each element in C is going to be squared. So if I have, let's look at what C is again. C is a small little matrix. Each element's going to be squared in this matrix. So we're going to have 1 here, 4 here, 9 here, and 16 here, right? So we're just squaring everything. Next, what we're going to do is we're going to divide by the square root of 10 times D. D is also a matrix, so what we're going to be doing to it is multiplying each element by 10 and then taking the square root of each element multiplied by 10. So then take it all together, we're going to do, only because these matrices are of the same dimensions can we do this element-wise. We're going to take each element of C squared and then divide it by the corresponding element of the square root of 10 times D. And all of that is going to be passed to our signif function, and it's going to give us 3 significant figures. Okay, so let's do that and see what it looks like. Okay, so let's walk through just the first entry to make sure we're clear on what this did. C, our first entry is 1, so we can do this literally per entry and just walk through it, right? So we have 1 squared is 1 divided by the square root of 10 times 10, which the square root of 10 times 10 is the square root of 100, which is 10. So this is 1 divided by 10, and it's showing us 3 significant figures of that value, because 1 divided by 10 is 0.1. But because of our signif function and 3, that's why you have 0.100. Okay. Right. So I'm not going to walk through all the other ones because I probably can't get the square roots of them as easily in my head, but it's doing this exact same thing. It's just performing these things element-wise per each matrix, and it's doing that because the matrices C and D are of the same dimensions. Okay. So we can also update individual elements of our matrix the exact same way we did that in our vectors. So here, again, I'm not using capital T as a object because it is, again, in my opinion, not a good thing to do. So I'm doing double T instead. So double T is going to take a matrix where it's going to get 2 repeating 45 times. And we're going to have 5 rows. So let's do that. Let's also look at what that looks like just to, be clear. So it's just this 5-row matrix of all 2s. The rep function just repeats whatever the first number is for how many times you specify in the second number. Okay. So the same way that we did with vectors, where we could specify the location of the number we wanted to change or the element we wanted to change, we do the same with matrices, except we have to pass it both our row number and column number. So we have double T, row 4, column 2. It's going to be specifically this 2 right here. We're just going to pass that the number 8. So now if we look at it, we can see everything's the same except for row 4, column 2 now has an 8 in it. And that's because of this line of code right here. Okay, So we can do that with entire rows and columns if we'd like to. So now, again, as we saw in the example before, we're going to specify our row number, leave our column number blank, and this is essentially going to say the row number across all columns. So double T, row 1 across all columns is going to get the sequence of 1 through 9 incrementing by 1. So if we do that and check what we get, we can see now our first row, the entire row, has been replaced with 1 through 9. Okay, just one quick note that I want to mention. It is important, like these examples have been written so that all the dimensions make sense, but once you start to get into, especially like matrices and more, having your replacement dimensions and your, the dimensions of what you're replacing equal to each other, that's really important. So here, the sequence of 1 through 9 is the same length as my first row. And it's important that once you start doing this on your own, that you actually keep this in mind if you're doing it from scratch and not just following an example. Okay, so lastly, we're just going to cover the apply function. It's pretty simple. It applies a function to a matrix either by column or by row, and that has to do with the middle number that you're specifying. So let's remind ourselves what matrix G is. It is this. Okay, so we're going to do apply G to var, and what we get is variance applied to our matrix G, and specifically applied to the columns. That's what this number 2 is about. So we're going through each column and taking the variance of it. It's basically like a more general version of those call sums and row sums that we found. It can apply whatever function, as long as it's appropriate, to all of your columns and all of your rows. So next we could do an apply to G, taking the median of it to the rows, which is what 1 specifies. So for this middle number here, you have either a 1 or a 2. 1 means you're applying it to rows, 2 means you're applying it to columns. So it's apply whatever your matrix is, whether you're applying it to rows or columns, and then what the function is that you're applying. If we do that, we know there's only 2 rows, so what it's done is it's taken the median of each row. The median of the first row is 8, the median of the second row is 16. Okay, so that is it for matrices. I will see you all for the next video.